Hi friends, today let's talk about optimizers. First thing first, why do we need an optimizer? In a typical machine learning model, you have forward and backward propagation. After the forward propagation, the model has its own prediction. It then uses loss function to quantify the delta between the prediction and the true label. After that, it will go through the backward propagation, where it calculates the gradient of the loss over the weight. So with the gradient, the model now knows which direction it should adjust the weight. However, there are still questions remain to be answered. First of all, regarding the direction, we already know how big of a step should we adjust the weight. Also, how do we smooth the noise? So these three questions are what optimizers are aiming to solve. So today, we're going to talk about 5 optimizers from the most vanilla one, gradient descent, to momentum, to AdaGrad, and then to RMSProp, to AdamW. So let's get started. We will first talk about gradient descent. It is actually the first thing you can ever do once you have a gradient. So we'll use W to represent the weight and DW to represent the gradient. Essentially, with gradient descent, what you are doing is just adjust the weight towards the gradient. So LR represents learning rate. So it just means that we're stepping towards the gradient direction, but only a small fraction of it. Then notice there's actually a problem with the gradient descent. It always reacts on the present. It doesn't take consideration of history. So that is why there's momentum. In momentum, there's this concept of velocity. Velocity is exponential moving average of the gradient. It is expressed like this. As you can see, you can use beta to tune how much you want to consider the past and how much you want to consider the present gradient. It is able to keep track of all the history and also being bounded because this is 1 minus beta here. So with the velocity, you can see W equals to W minus LR V. Instead of directly moving at the direction of the gradient, we are moving at the exponential average of the gradient, which considers the historical steps of the gradient. Momentum has this concept of velocity, which when you look at it, is actually the exponential average. It's a concept of the mean. So AdaGrad introduced another concept about the variance. AdaGrad also takes a look at the historical steps. It looks at AdamW's square of the gradient and it aggregates them. So what it does is that, so it has G equals to G plus DW square. So it keeps aggregating the AdamY square and then it uses it to update the W. The intuition is that in your weight vector, every element have different gradient value. Some gradient can be large, some gradient can be small. By normalizing element-wise, you are able to have each direction moving at a relatively similar update size. So, for example, if one element is very large, but historically it is also very large, the true value, and you do this normalization using square root G, if you bring down the volume of the large gradient. Similarly, if your gradient is small, with the square root of G, it is able to increase the volume for the smaller gradient. But now, you see this problem here, right? In AdaGrad, there's actually one severe problem, is that the G keeps increasing monotonically. Think about if you go to 1,000 steps, more than 1,000 steps, G will become increasingly large, and then each step here, the update will be increasingly small. So eventually, it will bring down the update, causing the weight to stagnate. That is why we have RMSProp. In RMSProp, what we are doing is that instead of letting G go unbounded, we're using the same concept of momentum. So we're doing a moving average for G. So now I guess you can see some pattern. In momentum, we're doing moving average for velocity. And in RMSProp, we're doing moving average for the DW square. So this represents mean and this represents variance. So Adam is a combination of momentum and RMSProp. It does moving average both for DW and DW square. It considers both mean and variance. How did they do so? So first, it does the moving average for variance, and then it does moving average for DW. So similarly as before, it will use square root G to regulate the update steps. It will use V to replace DW. With that, Adam is able to combine the good side of both momentum and RMSProp. So lastly, we'll talk about AdamW. AdamW basically is Adam plus weight decay. So only difference here, as you can see, is this term. So this is an additional weight decay term. In Adam, weight decays is actually incorporated in DW, but AdamW, it decouples the weight decay out of DW in Adam. The benefit is that before it is decoupled, the weight decay is also factored in the adaptive method of exponential average. But now it is independent. The weight decay is independent from the exponential average. So every parameter right now get the same relative regularization strengths independent of the gradient history. So lastly, I want to share some visual intuitions about these different optimizers. First of all, we can look at how a momentum adds up to the gradient descent. So here, we're optimizing the Rosenbrock function. These three different optimizers, gradient descent, momentum, they start from the same starting position. As you can see, the pink line is the gradient descent. The orange one and the purple one, they're both momentum. So the orange one has momentum beta equals to 0.5, and the purple one has 0.9. The bigger the beta, velocity will take more consideration into historical data. So as you can see, because beta is bigger for the purple line, it still remembers the old direction. That's why it is going this way, even though the gradient descent says you can go up. This is not to say that momentum is not helpful. Momentum is actually helpful when there is noise in the gradient, and in this case, the change of the gradient is not noise, so it takes momentum method a few steps to catch up, but it will eventually still getting back to the right direction. Next, let's compare AdaGrad versus RMSProp. So for the same number of steps, as you can see, AdaGrad is a pink line, and the RMSProp is the orange line. The fatal drawback of AdaGrad is that its weights will eventually die out as the number of steps going on. So this is actually reflected here. So for the same number of steps, RMSProp is still going towards the global minimum, but AdaGrad is actually stuck here. So as you can see, with the exponential average, RMSProp is effectively avoiding the drawback of AdaGrad. And lastly, we're comparing Adam versus Adam with weight decay. So these two paths, pink line is Adam, and orange line is Adam with weight decay. As you can see, at the beginning, they're starting very similar, but with weight decay as a regularizer, AdamW is able to go towards the global minimum faster than Adam. So now let's put together of everything. We have talked about these 6 optimizers, and now we'll put them together and see how they converge and get towards the global minimum. So we start from number of steps equal to 500. So right now we can see that these 3 optimizers, they are far superior than the rest. You can also see it from the function landscape here. So these are the gradient descent and the momentum. The pink one is Adam, this is AdamW, and this is RMSProp, and this is our global minimum. So remember, RMSProps only have exponential average for the variance. You can actually see there's noise here compared to Adam and AdamW. So here is the landscape here. As we can see, the final XY right now, the minimum is RMSProp. RMSProp is closest to the global minimum. Now let's look at number of steps. It's 1,000. As you can see, AdamW is closer to the global minimum. For momentum methods and gradient descent, they're still kind of here. They're not moving aggressively towards the global minimum. For Adam, it's still figuring out where is the global minimum. So now number of steps is 2,000. Adam is still here. Nothing really changed except for the momentum method is getting closer to the global minimum. So 5,000 steps here right now. Finally, Adam was able to detect actually it should change its direction. So what happens at 10K step right now is that you see Adam is quickly catching up and getting closer to the global minimum. So eventually we get to 20K steps. At this point, we can see the clear winner is AdamW. But except for AdamW, gradient descent momentum many methods have reached to closer to the global minimum. As you can see here, these are the gradient methods, and Adam and AdamW was able to get closer to the global minimum. So you can see here, the global minimum is close to 1,1, and Adam and AdamW is the closest. Here is a visual comparison of the winners. So AdamW clearly wins. We talk about why do we need optimizers. Essentially, after we have the gradient, we need to know how big of update we need to make for the weight to make the prediction closer to the target. And then we go through the evolution of the optimizers, starting from the gradient descent. The gradient descent only takes consideration into the current gradient, which is prone to noise. That is why the first improvement was on momentum. Momentum essentially introduced this concept of velocity. It is an exponential average of the gradient that takes consideration of the historical data. And then the other direction is AdaGrad, which takes consideration of the variance. So momentum is the analogy for the mean, whereas AdaGrad goes to the direction of looking into the variance. AdaGrad is good, but has this fatal drawback where the updates eventually get stuck because it keeps accumulating the square of the gradient. That is why RMSProp was introduced. It also uses exponential average, but it applies exponential average to the variance. RMSProp was able to solve the drawback of AdaGrad. Now we have the momentum, which applies exponential average on the gradient itself. And we have RMSProp, which applies exponential average on the square of the gradient. So Adam is actually combines both. Adam applies exponential average not only on the gradient, but also on the square of the gradient. So you can think about this as Adam considers both the velocity and also the acceleration, both the mean and the variance. So AdamW is essentially just Adam plus a weight regularization with weight decay. So in recent years, Adam and AdamW has become the standards. So that's it for today. Thank you for watching. Let me know what you think.